wireless SCADA attacks.
Greetings, everyone. How are y'all? Thanks for waking up at the butt crack of noon just to come see me. I really appreciate it. I know I saw a lot of you guys out partying last night pretty hard, and I heard stories of, oh yeah, I looked at my watch and it was 6:30, and I decided it was time to go to bed. What? That was none of you? Yeah. So today we're going to talk about just a few fun things about SCADA, and particularly the state of SCADA wireless communication systems. Then we'll have a little deep dive into some hardware hacking that really has more to do with what's possible with hardware hacking and less to do with any one particular SCADA system. If you've heard press about my talk in the past, I'm so sorry that you'll be very disappointed. It's not nearly as glitzy and amazing and horrible as it's been made out to be. But hopefully, if you are interested in some of the things going on in the SCADA world and have a technical bent and desire to see cool, hacky things, you will be happier. Little intro to me. I'm a doer of stuff. I love to do stuff. I also have some kids and a wife. As I said, I'm a doer of stuff. I'm addicted to electricity. All of my hacking requires it. Well, except for the physical pen testing, but that's a different story. I am into binary. I like zeros and ones. I like anything that can be looking at something a way that most people won't. Who here has some experience with understanding, at least, the way that our power grid is put together? About a fifth of you. Good. Okay, for the rest of you, we have lots of power that flows over lots of lines, right? And that's power grid. Shucks, there's a little more to it than that. There are control systems which monitor lines, watch how much energy is being used, watch how much is being lost, and heaven forbid, when that tree or Billy backhoe takes out power, there are things to cut off the broken section and keep power to the rest of us. So if you've ever lost power for, I don't know, like 2 minutes or a minute, and then have it come back, probably something has happened to a line somewhere, and the automated systems or the people in the operations center said, ah! And a recloser said, okay, we're going to keep this circuit going over here and this circuit going over here, and we'll go send somebody out to go try not to get fried. How many of you have an idea of at least one power substation nearby your house? That's a much better number. Thank you. You're the hackers that I intended to be speaking to, those who are aware. I know where about 3 or 4 are very close to my house. These substations, by golly, there are computer systems there. There are control systems. They cost money. I'm not going to delve heavily into it, but the power industry is a heavily regulated private industry. I don't know if that like warped your mind too much to say those 2 words in the same sentence. But in order to charge more, a power utility, which is a company, not the government, has to go to their government regulation people and say, we need to charge more for electricity because of this. You have government officials looking out for your best interest. At least they're trying to. Okay? Let me let that sink in. No shmoo balls? Yes, I said it. So am I. Hold on a second.
We're from the government and we're here to help.
I knew that about you. I saw that yesterday, that little glint in your eye. So, no, she's an engineer, so there's good stuff there. So anyway, there's a company trying to make some money, a government entity telling them exactly how much money they can make, and so Who here has any telecom experience? How much does a lease line cost? Lots. It's a recurring cost, right? How many does maybe 100,000 or so? Lots and lots and lots. So many substations have moved to a wireless communication mechanism so that they don't have to pay the lease line costs. And since it's a recurring cost, they can make more money. They can save you money. That's the real pitch. So this is where we are. Now, there is one solution for all of the power grid that you go to the power grid approved store and you buy this one wireless solution, and it has wonderful hard crypto and universal interface and provides support for every known power grid communications protocol, and it costs really nothing, very little. Come on, I'm lying through my teeth. Thank you. I was hoping to collect 10 or more take home to my kids. No, bullshit. There are a bunch of vendors trying to make a buck in this industry, squeezing out their engineering staff to deliver low-cost solutions that they can mark up and make some money on, and then, you know, it's a very convoluted marketplace. So we see a whole lot of technologies in wireless in SCADA system. Now, excuse me, who here's heard of smart grid? Let me do a little bit more clarification before I move on. Smart grid, it's the idea, it's the movement to bring more intelligence into our grid. Intelligence, AKA microcontrollers, AKA computer systems, to do more intelligent things. Really good idea, really adding a lot of risk. I mean, in the risk analysis thing, it adds risk because, well, we all know what computer systems can do. Smart grid is made up of a bunch of different components. You will hear a lot about smart metering. And smart metering is not the kind of communications that I'm talking about here, because each smart meters have gone out, invested a lot of capital into their own proprietary, mumbo-jumbo thing that makes them able to mesh millions of meters and control them. What I'm talking about is the substation backhaul, which tend to be a very different technology set. So we have a lot of sub-gigahertz wireless proprietary protocols. Proprietary, yay, right? Interesting stuff for us. Not been done before type stuff. They do have some 802.11 and a bit more 802.16 WiMAX, the long distance equivalent to Wi-Fi. There's some Zigbee and 802.15.4, which Zigbee is based on. There is, there's reusing of 3G and cellular. So there's a lot of cellular modems being put into gear and plugged into this, this beautiful panacea of networking that is protected by a chain link fence, maybe. Sometimes this is done well. I will say that right now. Sometimes it's done well. Sometimes there's a lot of obscurity being relied upon or false assumptions. For example, I just called out the chain link fence thing. That's secure. I live in BFE. I can't even see my neighbor. In the substations I just called out, nobody would see if I hopped the fence. More on that in a minute. I also want to call out, before you go freaking out, the local SCADA communications, the stuff that says I have to have sub-millisecond response or sub-50 millisecond response, or something actually goes boom. That is all typically local and not done over wireless communications. So, that said, I want to move on into the communications and control stuff, but those things that are very time sensitive, at least I'm hoping. I have to take it on faith, but I'm hoping that they are actually just local. There are a few common radios I'm going to talk about here, not in any real depth, but just to give you a lay of the land of some of the exemplary radios. There's a Raven X that uses the cellular technology. Silver Springs makes an E bridge and an S bridge as well. We'll just give pictures and a couple details in a minute. XtendRF is a is Digi's entry. Who here knows of Digi International? Not DigiKey, but Digi. So, what's that? Yes, so like your Mac Stream, your Zigbee on your Arduino, that's Digi. So Digi has their own radios that are widely used in power grid. And then we'll talk a little bit about a radio called SpeedNet. And somebody here has heard of Syseco, right? They're a little lesser known player, more of a hobbyist type radio that still has found their way into power systems. One of the interesting things when I first got introduced to some power people was just how hackerish the engineers are. They are all about getting it done in the way that they need it done, based on their use case, their business case, and their political bent. So Syseco is a little more maybe Arduino-esque than some of these others who have bigger, more marketed products, but they're also being used as well. I've made an RfCat out of one of the Syseco tools. Actually, it's pretty cool. Yes, thank you. Picture of the Raven X. You're going to get used to this footprint. This is pretty common. Raven X has an Ethernet 10100 jack, and they use 3G CDMA, blah, 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 and also a DB9 to basically just bridge the wireless. Plug in this thing here, plug in that thing there, and we've got a serial port. It just works. They even include an IPsec VPN, implemented by somebody I do not know and have no idea how well they did, or at least for the purposes of this talk. Actually, one of the big hitters in the field here, Silver Spring. They live in the sub-gigahertz range, 902 to 928 specifically. The eBridge comes with one Ethernet, one serial. They do the same thing, just a straight through. Hey, right here, right there, point to point, okay, with the Ethernet stuff, there's some interesting stuff you can do there. But the S-Bridge is just a serial straight through. So much of the power industry uses serial communication because it just makes sense. It's from 50 years ago, and when they first came up with serial communication, like flicking up the feather on a bird and then flicking it down for a zero. These guys worked between 2400 baud and 115K, so pretty good range there. They include an embedded firewall and IPsec tunneling. Honestly, of the vendors that I'm going to cover, these guys probably have it the best going on. I wish that their engineers and their security team would go talk to their marketing team, because this right here is kind of funny and, well, wrong. Digi. Very hobby-esque. Also sub-gigahertz. They sport a watt of power and they claim to have up to 40 miles of range. They're basically a serial bump in the wire. You plug it in here, plug it in there, and it's like there's no wireless at all. In fact, that's the way they like to think of it, actually. They use 256 whole bits of AES encryption, which is pretty good. Where they store those keys and how easily accessible they are, I will not talk about. They have 10 whole hopping patterns. Now, look. Think of this phrase right here from this vendor. And now apply it to this vendor with their entire 10 whole hopping patterns. Unique. You can even have another utility using the same device with a different hopping pattern that won't interfere with your stuff. And really, legitimately, that's why they offer 10 hopping patterns. It's not a security thing. Here's the twist of the vendor story. SpeedNet is a widely used, also sub-gigahertz radio that they use 51-channel FHSS, which means that they can read the FCC spec that says you have to have over 50 channels to use the greater power that you get from using hopping. Basically, the FCC says you're limited to using, I forget what it is, like 0.1 watt? Somebody correct me. If you're doing a straight one-channel usage thing. If you spread out over an entire spectrum, the 902 to 928, and you break it up into more than 50 channels, and then spend less than 0.4 seconds on any one channel in a 20-second period, yes, it's that specific, then you can use up to 1 watt. Huge improvement, and this is the reason that frequency hopping is used widely in the industry. It's not the security feature. That was probably added on to the marketing spin. 1 watt of power. They can go up to 25 miles. They use forward error correction, 128 whole bits of AES encryption, probably stored in an EEPROM somewhere. Military grade. Okay, this is where we get into troubles. Oh, wait, no, this is NovaRoam. NovaRoam, I'm sorry, I got it wrong. It looks so much like, oh my gosh, it is. SpeedNet and NovaRoam are the same thing. In fact, this is a problem. Because SpeedNet is used heavily in the power industry. NovaRoam is used in, well, maybe more clandestine uses. Maybe, I don't know, military. Military grade, yes, NovaRoam is. Problem is, when you find a bug, how easy do you think it is to fix the bug? How easy do you think it is to communicate the bug? Well, I'm here to tell you it is not easy. In fact, there's a whole lot of, holy crap, we got a ton of those out there. You can't talk about this. What? I think somebody missed the point. So the question was put to me when I was putting together this talk. What would you do? How would you attack this? A couple of different ways. There's a lot of fun to be had. I do not recommend this. I'm not saying it's okay. It is just as illegal in your state as it is in mine. And it is trespassing, and you could get electrocuted or prosecuted. Which one is worse, I have no idea. Hop the fence into the substation. Many of these substations are just a chain link fence wrapped around some scary-looking power equipment and a box that happens to have all sorts of goodness. What kind of goodness, might you ask? Well, there are the control systems that control the reclosers, monitor the use of electricity, and watch for problems. What can I do with that? If I can maybe create some indicators of problems, I can cause the people back in the operations center to do things that cause big problems. Whoops. Let's see, what else? I can manipulate the control systems. I can cause them to do things. And, oh, lo and behold, one of my favorites is, there's a point-to-point radio there with an Ethernet jack. I'm not even going to go into that one. You can use your imagination. So this doesn't even matter if that's a wireless connection or a lease line. I mean, this is a problem that they have to fix or just at least accept the risk. And you guys, some of you, I'm sure, somebody in this room will be doing research and security work for the power system. So have fun with that. Be very safe. Be very upfront, transparent, and do good things. I love my power. I want these things to be well protected. Another thing that I might do is grab a pole top device. In the power industry, it seems like they think that poles are security devices. So they stick these basically unprotected devices in a box that requires a special key that nobody here could crack into. And oftentimes, it is a device thingy that talks to a whole bunch of other device thingies with an Ethernet cable going to some other device thingy that has a backhaul back into the utility. I would love to pen test one of those. How many here would like, nah, I'm not even going to, no show of hands. But I would just venture a guess that there are a couple utilities who probably just allow that traffic in. Could you hear me? Could you hear me? What's that? They can? Some of them? At that point, does it matter? I think the power grid in the Northeast probably was a good example of how much attention can be sometimes paid to such alarms. But yes, there are things in place to at least alert sometimes. But that still allows me access to the hardware. It allows me to grab something to go reverse engineer. A buddy of mine, when I was referencing, just trying to make sure that I'm not talking too much bullshit, I sent this off to a buddy, and he said, why even climb the tower? Just shoot it down. Because these things have a battery backup, or a high capacitance capacitor that gives like 24 hours of power for the things, so it keeps running after you can get it off the pole. And of course, what we're here to talk about is RF hacking. Radio analysis. Let's see. There are a couple different parts of RF hacking that I want to talk about. There's radio analysis. How do I actually attack the system without ever touching it? So I go local, I get wireless signal, I become part of the network, and then I can start attacking various devices. Again, only do this legally, do this with the help of your utility, not against. Part of this, and some of the other things that can be done, involve hardware reversing. So we take the device, we slam it down, we do hardware-y type things, and we'll talk a little bit about that in a few minutes. And we find out things that we can do, how we can interact, other vulnerabilities that might be there, including such things as maybe, I don't know, hard-coded keys that are in the firmware. I'm going to say this now, I'll probably say it a couple more times. The wireless comms are not our biggest problem with SCADA systems. They're just the focus of my talk right now. We have a lot of things to fix. But how do I diffuse that? I can't do it right now. Maybe later. Another approach to hacking the wireless would be to repurpose hardware. So let's say I grab a communications board. I use the firmware that's installed to monitor and learn how the radio hops around. And then maybe even use its configuration, all the while tapped onto a control bus for the radio. And when it's all set up the way that I want it, I just hold the reset pin on the microcontroller that's driving the radio, and now I can drive the radio. It's like, thank you. It's kind of like a marriage thing, you know, the father walks the bride down and then like hands it off to There are other things that you can do with repurposing the radios, namely, some radios have a module that you can buy separate from the radio, and the module implements the thing that does the radio stuff, and then all the configuration and user interface stuff is wrapped around it, and the module is just kind of soldered hard down onto a board, and you can oftentimes, again, let the microcontroller trigger and set up that module and then take it over, or you can just take it off and wire it into your own tools. And then there are some devices that just, you can go buy COTS equipment to go talk to. There's an entire document about how to do hardware hacking. It was written specifically for the purposes of testing and validating the security of the advanced metering infrastructure. I said, you know, these are different types of things. But the same principles can apply here. A couple of guys from InGuardians, you can go download this from their website. There's the link. But it talks about reconnaissance. How do you learn about the system? How do you break down what interesting things there are? There's analysis, the simple analysis and then the deep analysis. So like dumping EEPROMs and then doing analysis of the data that's on there, because EEPROMs don't come with any particular security mechanism. It talks about other radio type things, all sorts of fun stuff. I just like the pictures. So we've got a USRP radio here, a software-defined radio. Here's the heroin needles of doom. Travis is very well known for. And here's an example of one with a pair of LEDs. One will light up if you're getting data going one direction, another will light up if you get data going the other direction. It's kind of fun. But it talks about bus snooping, and that's where you get on the bus, the wires in between microcontroller and radio, or other components, the EEPROM or whatever, and watch as data is pulled. For example, I knew one vendor that had, it stored some crypto keys, and then their response to me when I asked them about it was, don't worry, we store the crypto keys non-sequentially on the EEPROM. But you get them all at the same time, right? Well, yeah, we get them when we need them. So the address where the bytes live don't matter, but if I'm snooping the bus and I can put the bytes back together, thank you. So I won't dwell too much on that. That's good work. You should check it out yourself. Intro to hardware hacking is basically what it should be called. I've talked to people, I think, in this room who have come up to me and said, hey, dude, you got to check this out. This taught me a ton. So yeah, I very verified, something like that. They did a good job. Radio analysis. When we get into radio analysis, what's our goal? There are a couple things that we can do to a radio system. First of all, we can jam it. Yeah, denial of service! I'm so powerful. This is like 1991 of, the press a button and you kill a machine. It's the same thing here. You can do it with wireless. You will always be able to jam wireless in some way if you've got the equipment and the knowledge. But I prefer the idea of creating an attack radio. Let's get my computer onto the mesh. You got the information superhighway. This is the information, like, back road. But when you're talking 100 kilobaud, it's a little different. So I've done a lot of research into building Mac and PHYs on radios. So the spectrum used, how it's used, modulation, baud rate, stuff like this. You remember, anybody have a modem when you were a kid or sucking on a budsicle? Well, a lot of the same terminologies and ideas that went into your modems, the baud rate and stuff like that, they apply here as well. And then Mac intricacies. So things like, how often do we change channels in a frequency hopping system? What determines what that next channel is? Because when you can figure those things out, you can have a tool from which you can then actually launch attacks and test, validate, verify, make sure they're doing their shit right. Because in this room, I'm hoping that is actually your goal. We're not here to break things, particularly the power grid. I like my power. Except in a controlled environment where breaking things can make the things that we depend on better. Once you've got the hardware, pulling firmware is a great thing. It can tell you a whole lot about how the thing works. It can tell you a whole lot about how it interacts with the radio. It can tell you about hopping patterns. And of course, it can tell you about vulnerabilities. I have had the extreme pleasure in the last few weeks of learning that RfCat, my tool, has been used to launch ODE against an embedded system using actual vendor code, not like, a crack me, to land ODE. It made me very happy. That was the goal of RfCat, was to take responsible security vendors and get them close enough so that they can do great things. Some of the security measures you may have heard of that are being used in SCADA comms, crypto, authentication. There are a couple weirder ones that are being relied upon that I want to call out. Frequency hopping spread spectrum is still somewhat, by some people, considered a security mechanism. Some people are rolling their own proprietary crypto. Yay, WEP, that's a great plan. And proprietary modulation. Apparently we've got some RF engineers involved. Yes, lots. I'm going to do this a few more times, I think. We have lots of RF engineers. We have lots of engineers that are thinking really great things. And sometimes, apparently a couple times, they've come up with their own modulation scheme that makes their stuff unhackable. And what do I think of reusing technology? We'll talk about that. A few years back, I had a vendor at a booth that I was engaging in a security conversation tell me, when I probed them about their security, they said, well, our frequency hopping spread spectrum is too fast for hackers to hack. What? There is some sort of disconnect in the brain or in his training or something, but I've heard it multiple times. And in fact, you can tell from the slide just a few slides ago, there's been this interesting idea that frequency hopping is for security. I read it in a patent from another very actually prominent and well-placed, well-securityed smart grid vendor that we believe, this was years ago, but we believe that our frequency hopping spread spectrum is sufficient security to defer or defend against attacks, and it's in patentees. And I went to the guy who wrote it, and I said, really? He said, well, it was patented back in 2006. Okay, this is a great plan. Commercial-grade frequency hopping is not the same as the military-grade frequency hopping. I know when we did our hack hopping heady talk a couple years ago, we had a ton of like DoD.mil type people showing up going, they've broken frequency hopping. Well, no, we've advanced the research into determining frequency patterns and tried to at least call out some of the things that are less than true. So, for example, yeah, no, I won't go there. So, hopping patterns can be determined by a number of different ways. Reverse engineering the hardware, getting the firmware off of it, and looking through the code as it determines what that next hop is going to be. Patents and FCC documents are amazing for this, particularly if you have a forerunner in the industry that thinks our stuff smells like roses. They're very happy to call out, we do it this way, in this exemplary model. You have to learn how to read patents. Because they don't talk like normal English people. They talk like engineers turned lawyers. It's a little scary. But in the exemplary model, we choose a hopping pattern based on this and this and this and this and this, and this is how it's done, and because it's very good to have it out there so that, hey, if you do this thing, you're going to have to pay us. Which is good for us, and actually it's good for the industry. I'll poke fun at everybody. But in reality, hiding that stuff is not security. Let's just kind of dispel the whole myth of any frequency hopping security, period. Blah. Let's make it so that we can develop tools that we can go test. Because let's prove that it's secure. Radio analysis, bus sniffing. Bus sniffing is very fun. We're going to talk a lot about it in a couple minutes. So, actually right now, deep dive into hardware hacking. The following slides are basically just some of the research that I've been doing against a particular product that I've had a lot of enjoyment recently for breaking for analyzing. We're going to talk about using GoodFET just a little bit to dump firmware. Very, very little bit. You guys went to Travis's talk, right? Travis Goodspeed made the GoodFET. We're going to get into a logic analyzer and then analyzing the logic. RfCat packet dump and firmware analysis. Just a little bit of each. Okay, a lot of some of it. So this particular vendor that I've been playing with their product chose a chip that absolutely has no ability to secure the JTAG, the debugging ports. This is the first step in any analysis of a hardware device. And I was very happy to find this. A lot of vendors, they have the ability and they just don't turn it on. Those are the ones I roast. But these guys, I think that they had some design reasons why they want to do this, so I was happily able to pull off firmware. That's good stuff. You know, in fact, a few friends of mine have been working on doing JTAG for ARM code, particularly targeting chips very much like the one that I've been attacking. Bus sniffing was a little bit harder. This vendor has very, very fine, tight pins on their microcontrollers and all around their boards. So even heroin needles kind of slide off, and they're really hard to tap down. And so 20 bucks a piece on sale. They're 40 bucks a piece retail. Micro grippers. You buy them in packs of 10. Yes, $400. That's why it took me a little while to get some. So I finally bit the bullet, attached them, and let bus sniffing commence. There are two different buses on this device. They've got a config bus, and they've got the data bus. And so you see the radio configuration get set up over the config bus, and then you see the radio data transmitted over the second. It's actually pretty clean, nice to look at. And the big picture. Here is a bus sniff capture off of this device that probably lasted, I don't know, 15 seconds. There's a lot of ups and downs there. So the top three are a radio configuration SPI bus. Who here is familiar with SPI? One protocol, right? No variances. You just slam it down. Yeah, the protocol is a wire signaling protocol, and everything is different. Everybody does their own thing. You basically have to read the data sheet of the thing you're trying to talk to. This is this is one of the best logic analyzers that I've ever run into. It is made by a company called Celea, and I would like to promote their business because they are doing really awesome work, and they've helped me a lot. The bottom pins here are the data pins. You see they're really hard packed together. We'll talk about that a little bit. Zoom in just a bit, and here we see at the top radio configuration stuff, placing the radio in receive mode at a particular frequency. We then see a lot of crap down here. This bottom is the clock, so its crap is going to be pretty continuous, at least until they're sending data. But the way that the ADF radio that they chose works is basically you put it in receive mode, and then the thing generates clock at the rate that you tell it to, and it sends you bits all the time. Now, many radios, if you've been paying attention to RfCat, many radios will have a packetizer and will look for a sync word and look for, the start of frame delimiter, SFD. It's also known as a sync word. It's just some bits that after a particular amount of ups and downs in a right pattern, the radio, not your code, but the radio says, boom, we're at the beginning of a frame. Let's go capture this frame. And then when we're done, we'll hand it off and have it be processed. Really great stuff. With this radio, they had to write their own code to do that because the radio just says, oh, baby, I got bits. I'm sending you bits. Yeah, bits. A little bit deeper dive into the config info. The top line is the enable pin. Basically, when the enable pin goes low, it's driven low, meaning enable. That tells the chip, I am controlling you. Listen to me. Luke, I am your father. Change to 903 megahertz. Second line is the clock line. So you see the enable pin drop low. And then we send clock at a pretty consistent rate. And then based on where the data line is at each clock, the radio knows what data to receive. Digging into the ADF 7020 data sheet, you're able to see what these bytes mean and understand the configuration of the radio. So it's no longer magic at that point. Bus sniffing the data I/O pins is a very interesting task. This is the very high level. So we have the data up here, we have a clock up here. Just looks like a big white block, right? Well, let's zoom in just a little bit. Looks like a lot more white block with very specific exceptions here. We'll talk about the exceptions in just a minute. Let's dig in a bit farther. So the bottom, what you're looking at here is the capture exactly at a time when the device was transmitting. So basically, you've got a radio config right here that says, okay, change to this channel and transmit. The clock line goes dead. What? Well, this radio is very low level. It's kind of a hacker radio, actually. It just says, you know how fast you're supposed to send. Just send me bits at that rate and we'll be good. I'll modulate whatever you send me at the rate that you send it to me. Really kind of interesting from a hacker perspective, from a hacking perspective of the radio and the datacomms. Celia didn't know what to do at this point. It's going, yeah, there's nothing there. I got no clock, there's no bits. Yay! Diving in just a little bit deeper and closer. Let's see, did I miss anything on that slide? Okay, no. So a closer view again, we got the enable pin going low, got the clock pin going, and then the data, and we send in a 32-bit value, which is how the radio works. And that 32-bit value says, set your frequency to this and turn on transmit. Here's the data that we see down here. Oh, this is the data line, not the clock line, right? See the clock line go dead, and the data line go all the same, very, very consistent. What do you think that might be? Anybody, shout it out. Preamble. Preamble, very good. I have a GoodFET for you later, not populated, sorry. A preamble. In radio, how many radio engineers do we have in here? Even hobbyists? Raise your hand. Okay, for the rest of you, the preamble is a bit set of ones and zeros back and forth in a certain pattern to try to squelch out noise. So the sun sends us radio signal. We've got so much radio signal everywhere all the time that if we were just to look for this one thing of data, we would get a ton of noise. We would get many, many false positives. So in an attempt to squelch out the false positives, we look for a preamble, ups and downs at a particular rate, a certain number of them. And as soon as a certain number is reached, our sync word delimiter detector, the thing looking for a synchronization word, says, hey, I'm good, let's start looking. And then when it sees that sync word that determines the beginning of the packet, it then goes and reads in the packet. It still can cause false positives. You can still get a piece of noise once in a while, but this dramatically improves your radio transmit and receive. So yes, we start seeing a preamble down here. Problem. I really couldn't tell you where the preamble begins or how many preamble bits that they're sending because that's in the code and I haven't done code analysis at this point in the analysis. So what then? Well, I did some more research. I like patents, and I've learned how to read them. And so I did some more research on this vendor, and I found that they do have a sync word listed in a patent. It has had nothing to do with this device that I'm after, but there's something. So I note that, set it aside, and then when I get to the data analysis later, we'll see that they use the same sync word. Turns out this vendor actually uses this mesh technology to solve a bunch of different problems, and the ability to have one thing which has a whole bunch of long-distance hops, long-distance communication, to ride on some short hop mesh networking that may already exist, makes a good business case. And so totally makes sense that the sync word would be the same between a couple different products of theirs. Let's look a little bit more at the transmitted packet. So the sync word I was looking for, F3A0. Can anyone see F3A0 there? Look, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, a gap of zeros. What? That seems a little weird. Well, it turns out, no, you can't find F3A0 in there. You can find, however, the bit inverted version, which is 0CF5. And then once you see 03F5, if you're looking, you can see 0, and then 3 is 2 ones, right? 0, 0, 2, 1, 1. I'm sorry, C, 0C. 1, 1, 0, 0. I got my own thing backwards. And we see a 5, which is 0, 1, 0, 1. And then we see a 0 right there at the end. That's the starter frame. So if we back up, see these black marks here? That is a transmitted packet. And we start looking at the config lines, we see consistently a very similar gap between the config lines going active. We see a couple points where it's out of the pattern. But if you look down here, you'll notice the points where it's out of the pattern, there's a transmitted packet. So measuring the distance between the two lines shows us about 20 milliseconds. If we're changing every channel to receive every 20 milliseconds, what's that mean? Well, for those of you familiar with frequency hopping, that means it's got a 20 millisecond dwell time. Dwell time is the amount of time that it waits on a channel before hopping to the next one. This is actually, I believe this is also in their patent, but I wanted to call it out here because the idea is to show you what's pretty reasonable to do just using hardware. So since Saleha didn't break this down for me, I was able to just write some code. So Saleha dumps a whole bunch of zeros and ones. I wrote some Python code that went through and looked for that gap where there was no clock for longer than a certain threshold of time on the data pins. And I said, that's the beginning of a transmit packet. And then at the rate that I knew to be the case and the rate that I knew to be the capturing, I went through and I just self-analyzed like a modem would, async stuff. And I came out with this. By the way, you can see that I wrote some custom code to interpret the config data as well. So I got two scripts basically. The config data tells me how the radio is configured and then what each hopping sequence is, what the next frequency is. And then I get to see what was transmitted there. Now I don't see the F3A0 in that top packet. So let's shift it up 2 bits. So that'll keep us at AAAA. AAAA is actually what a preamble is supposed to look like. Still don't see it. Well, let's invert the bits. Because remember, we identified that we didn't see the sync word in the bits to begin with. So we invert the bits. We still don't see it. But if we shift it again 1 bit, we get AAAA and F3A0 at the same time. Take the configuration that I was able to pull out of the radio, put it into RfCat, and verify. So on the channel that is transmitted first, I set our RfCat to listen, and I get the same thing on both sides. Except for these two 32-bit values, but then they resync after each. That tells me I'm not off on my frequency, or I'm not off on my baud rate or anything like that that would cause a corruption of data. These are just two different packets, because I captured it on the bus first, and I captured it on the radio later. So those 32-bit sequences change each time that the packet is transmitted. There is a bit more analysis that I'm not including here. I'm still working on. There's some for error correction. There's some other bit type stuff that's going on because I'm not yet seeing what I expect, but the fact that I'm seeing the same on the radio and the bus means that I'm accurate. Since I keep talking about packets or patents, I wanted to throw up there. This is what a well-read, well-used patent looks like. Multicolored scribbles, notes, and sequence hopping sequence generation, slot to channel conversion. So, good stuff. I had an analysis. I'm just having fun with disassembling the firmware. A lot of low-level stuff in firmware that you don't get to see in the x86 user mode realm much, like actually setting up interrupts, things like that. So it is fun to see where the handlers are and digging into the stuff that actually causes, I don't know, like radio reconfigs and transmissions and stuff like that. That's done with a deep dive. A couple more minutes, and then I'll let you get out of here. Seen some proprietary crypto systems. Don't do it. You guys know that. I don't have to say that. Good systems are peer-reviewed and basically lambasted. You guys saw the research talk yesterday, I think, right? Yeah, they're academic. There's rigor. And even the ones that are well-proven, they get broken because people keep hammering on them. It's done in a very hostile environment that proves out this crypto mechanism, and then when it breaks, everybody knows it. And yes, that's a good thing, because when it breaks, you better get your shit fixed. There's none of this head in the sand. You can't do that. An example of why we don't muck with even tried and true crypto systems is WEP. They modified slightly this thing that exposed a couple bits here and there and used that as part of the synchronization process. Yay, this is a good plan. RC4 is a great crypto mechanism. They broke it. Plain and simple. Even tested and true crypto systems fail far before the worst case scenario. And the numbers that you get are worst case scenario for cracking. They're brute force, and they're expecting that that last attempt is going to be the one that is the real crypto key or however you're trying to break it. They don't take into account virtual supercomputers, clusters, shared workload. It basically boils down to how valuable is it that I get this information now? How long do I need to protect this information? There is a good reason why this process takes a long time. Don't try to ramrod that through. It's very important. If you have proprietary modulation, don't. This is an SDR created by Mike Osman. I don't know if he talked here this weekend, but he's amazing. Amazing guy, amazing technologist, amazing hacker. Yeah, I'm all about the clapping for Mike. He has also made a professional RfCat that is in final testing right now. He's calling it Yardstick 1. So as soon as he releases that, it's a goodbye. He included amps for both receive and transmit. Yeah, I'm liking that a lot. Reusing technology. If you've been coming to cons for any time at all, you know that Hikari is a very scary person. And there are several other researchers out there that are breaking your GSM, your CDMA, your WiMAX. Chris Padgett, a good friend of mine, also has been known to, actually he showed up at a con with an IMSI catcher and then played somebody's conversation and then told him to take the conversation outside the room, please. Tap and backhaul. This isn't so much This isn't so much wireless technology as your leased lines. Do keep in mind, leased lines are not secure inherently. People work at AT&T. They don't just have automatons doing like fixing and repair. There are real people there. They can screw with your stuff. They can see your stuff. At the end of the day, the reason that I'm giving the talk is that we have to validate the claims of security by all vendors. It's our bent. We're going to do it anyway, but we have to. It's our calling in life. So what can we do about all this stuff that I've been talking about? I took the approach from manufacturers and owner-operators, but I threw in something for you guys too, if you're not. Manufacturers, give us the good stuff. Make it so that we have some way to deploy this stuff well, so that we have some way to monitor and be able to tell when things are a little hinky. Provide maybe cost breaks for the comms and the SCADA gear itself so that we can build out good test labs and validate what we are doing and how bad it is. Make your shit withstand an Nmap scan. Sorry, this has nothing to do with a radio vendor. This has everything to do with your SCADA gear. Just stop already. Or don't stop because I Nmap scanned you. Maybe that's the term I should say. Don't be a douche. Go hack yourselves. Be good. Help us actually do things well. Owner-operators, use the good stuff. Demand it. You have the dollars. You have to actually be not only asking for the right stuff, but you have to know. That means probably you have to hire somebody in this room to come in and help you know that what they're saying is just not bullshit. Make sure that you have strong security posture on the utility side. These remote links, guess what? They're untrusted things. There's gear on the other end that you can't really, trust nobody else is on with their laptop. Third-party verification. Don't go to IBM or HP or Dell. They're big behemoths. Sorry, Hacker Joe. I know that probably isn't happy with you, but a couple guys on the screen, they do a pretty good job. Notice I call out Travis and his neighbors. Have good incident response procedures. Know what you're going to do when bad things happen so that you have some mechanism to respond with. It's not just fear, because more hackers are getting into the space. This is something that you have to be ready for. Be ready for forensics. Make sure that you have your engineers and your management working well together. I know that engineers don't do well on communicating well. So oftentimes a security analysis from an outside vendor can bridge the gap and take the engineer speak and put it into business stuff. Security architecture review. If you're a security-minded folk in the industry, don't be Chicken Little. Don't say, it's stupid, we can't do that, it's awful, evil, this is going to break, it's going to go up in flames. Speak in terms of risk. Speak in terms of things that the managers who actually have the control can weigh and measure the risk, because it's their responsibility, not yours. They're about to kick me off. Speak in terms of safety, reliability, money, and the Public Utilities Commission. And at the end, owner-operators have to design deployments cautiously and with knowledge and understanding of exploitation. Manufacturers got to provide us the tools to make secure deployments possible, trustworthy, and then not get upset when we don't believe it anyway. Hackers, go prove it. Thank you very much.